right. So this is about Kafi Streams, which, does it work? It's a bit echoing. Okay. Which is basically a Python library which helps you to do stream processing in a way which you couldn't do before, I think. Okay, and it's based on on another tool called Kafi and the Swiss Army knife of streaming, and that's why the Swiss Army knife is there. Okay, so let's be quick. It's a lot of content. First of all, I have to say I'm standing on the shoulders of giants, basically. So this library is basically lives because, or only exists because there's some geniuses behind it, not directly, but in my mind, or also directly. So one is Matthias Debusmann, that's the main guy now behind Kafka Streams. I mean, Kafka Streams has many developers, but no, he is the main guy. Frank McSherry is also an interesting person. He developed differential data flow in 2009-10 at Microsoft Research, which is also an inspiration for this theory of this guy, who looks a bit puzzled, Mihai Budiu. So he was the main guy behind, with Leonid Rizek, behind DBSP, database streaming theory, which came out. So the first paper was 2022. And this guy as well, Bruno Russi, so he wrote a Python implementation, which I'm using in my tool. So he's actually doing this as part of his PhD thesis now. So these are the giants I'm standing on. Hope they don't break. So my Kafka story first. So I started studying AI in 1995, did my PhD in 2006, multigraph, dependency grammar, computational linguistics stuff. I wanted to find a job in AI. Of course, there were no at the time. I went to SAP for some normal, mundane software development. And a couple of years into SAP, I found out about Kafka. That was about 2014. And then in 2016, Kafka Streams came around. And so this is again Matthias Debusmann on the left side, on the right side, and McDonald, both from Confluent. And I thought, this is great. I mean, this will change the database or the data world completely, and it will be omnipresent in a few years' time. It will take off. But then, it didn't, right? Not really. I mean, it did take off. I mean, Kafka Streams, for example, Flink, they're extremely popular. I mean, so many hundreds and thousands of downloads and so on. But still, it's a niche, right? So many people are trying to shy away because it's not so easy. So, but I wanted to find out why. I mean, like 3 years ago, I started to try to find out why isn't this getting traction, or the traction it deserves, in my opinion. And then I wrote this book with Hubert Dulay about streaming databases, where we try to find this out a little bit. And last summer, I wrote a blog post piece, which then kind of went viral at Confluent as well, where I basically criticized them a lot. And it's again the same question: why is streaming not mainstream yet, right? And I think I now know why. Kind of. And the problem of stream processing, why it isn't mainstream yet, is leaky abstractions. It's that. Now, because simple imagination experiment. Just close your eyes and think about this. So you would like to build a stream processing pipeline. Maybe for just joining a few topics or something. And then ingest into a database, whatever. Or because you even have a low latency use case, which is rare in between. So this should be easy, no? So you start using some popular stream processing tool, Kafka Streams, Flink. It works at first, it's cool, and then you get it to production. And then, you see, you can reopen your eyes. Right. Because the problem is, the problem that's plaguing stream processing, in my view, is that it's not just data engineering, but it's infra and data engineering. So you have to actually know too much about the deep inner optimizations and everything of these systems to actually be able to use them in production. And that's, I think, what the main reason why we haven't seen this explosion of streaming and stream processing, why IBM has been acquired by IBM, for example. I mean, it has a reason. Yeah. So that's kind of the problem, right? So you need to do infra work. You have a lot of concepts to understand to make it work. And so then maybe it doesn't even work still. So in Kafka Streams, it's a bit less. So you have things like co-partitioning, you might know this, or keying. Then you have these three concepts, or two, K-stream, K-table. You have the join semantics. Oh, that's interesting, right? You know, I worked with Florian Trosbach, like at SAP, at this beginning of my Kafka journey, and he wrote this blog post then, which is still important, and that's how he explains the join semantics of Kafka Streams, and it's incredibly hard to understand. It's a great blog post, though. Yeah. So things like suppress, grace period. I mean, there's more, of course. In Flink, you have, of course, watermarks. You have then optimizations like mini-batch, multi-join, which all have trade-offs themselves. Then you have concepts like allowed lateness, side inputs. I mean, you can read all this stuff, right? Broadcast joins. I don't even know what this is all about, but it's there. So in the end, you have to sync. To tune your sync, so you can choose between what kind of sync do I use. Will it be kind of a buffer, which like the upsert sync, or will it be the append only sync? And so you have to think about all these. It's massive, and it's growing. This list, right? And there's of course a list of concepts which you have to learn for both, like not just for Kafka Streams or Flink, for every classical, I would say, stream processing tool. I mean, there's many others, also Spark structured streaming, for example, right? I shouldn't go so hard, so quickly. So for example, there's RocksDB tuning, a big one for both, even more for Flink, I think. Eventual consistency. I mean, this means because they are eventually consistent. I mean, it's by design, but we'll soon see that this is also problematic. You need a concept called exactly one semantics. So everybody talking about stream processing tells you we need exactly one semantics. You'll see later in my tool, or not my tool, in this new theory, it just falls away. And you have non-determinism, right? So you have, I mean, depending on the configuration of your system, of your nodes, of your Flink nodes, for example, and I mean, so for every scenario you get different inputs, right? So some outputs you get some. So you have the same inputs, but because of all these timings and race conditions, in the end you get wildly different outputs. I mean, I don't call this deterministic, actually. So what happens then? Basically, many of these projects are stopped or not even come into existence because they are too expensive, too hard. I myself at Bosch, when I was working for them, I had a similar thing based on Kafka Streams, which was, when I went away, it was stopped and replaced by Spark batch jobs. So we need a new world formula. That's here. Okay. So, enter database stream processing, DBSP. I mean, the name is very clunky, but yeah, it's like it is. Could this be a way out? So, basically, during my research with Hubert Dulay on the book I showed earlier, we talked with a lot of people, like lots of people from the stream processing and streaming scene, including those from Materialize and Feldera. And Materialize, as you might know, is a streaming database, really. It's based on differential data flow from Frank McSherry, which was on the first slide, basically. and dating back to even earlier than 2013. That's the first paper here. Now, DBSP is based on, or Feldera, we also talked to these guys, Mihai and Leonid. That's actually kind of a simplification because they use differential data flow in VMware as an engine, actually the Rust engine from Frank McSherry. And they basically said it's too complicated, we have to simplify it. And then basically Mihai mostly and Leonid, they came up with DBSP, kind of a simplification, a cleaner theory than differential data flow, but still in the same spirit. Right, so, and the approach is different. It's not like classical stream processing that we know. It's not ad hoc, it's not based on append only, not on lists or streams in the Java stream sense. It's based on sets, on weighted sets, and then you put relational algebra around it. So now we focus on DBSP, on the simpler, cleaner version now, and just a few simple concepts here. You might have heard them now, but just to go through them again, it's quite important to understand them, but not absolutely necessary. Okay, but let's go. So the question really is, how do these systems interpret a stream? So what actually is a stream, right? Because, like I said, in a classical stream processor like Flink or Kafka Streams, whatever, I was saying these two, there's much more, many more. Basically, a stream is an unbounded stream of data, right? I mean, which it is in some sense, but if you view a stream as an unbounded stream of data, which you can't control, then you're already lost. That's kind of the thing. Because DBSP has a different approach. Basically, it considers, it's a mind shift, basically. It changes the view on how you interpret a stream inside the stream processing system. Right? Because for DBSP, streams have a meaning, right? The meaning is just deltas, right? So for them, a stream is, in a way, a changelog, right? And the mathematical foundation for this, you can read that in these papers, there's multiple versions of it. It's called Z-sets. And a Z-set sounds very, very fancy. It's basically just a simple function which basically just maps something, can be a JSON, can be a tuple, like a database row, can be anything. Just it maps anything to a weight. And a weight in this sense is basically, I mean, it looks like this. So you have, this is a Z-set, for example, right? So this is a Z-set. So A is the first anything or something, and B this is the other one. And this means that A appears once, and B appears twice. So it's not the order, so this is a bit unfortunate. So it could be 2, 1 as well. Yeah, so, but the weight is just how often does this element appear in the set, or in the Z set, right? And in this thing, so now you can say that a deletion actually is a negative weight, right? So when you want to delete one of these elements, so when you, for example, you have a database row which is deleted in your Debezium change data capture system, which comes into DBSP, then this is a deletion that's a -1 for that element, for that something. So this is an example here. Oops, because when you combine Z-sets, when you integrate them in the DBSP sense, you just sum up the weights, right? So now let me try to do this. So basically, we have this Z-set from above again, where A appears once and B twice, right? So this comes into the system, we integrate, nothing happens, the same output. Then we have this change, this delta, that B gets deleted, right? Then we just subtract it from the 2 here, and we end up with A1, B1. And we get another deletion, and then it's A1, B0. And then the B kind of can be garbage collected, right? So that's all. Right? So that's kind of the thing. It's like, it sounds so innocent, right? Or looks so innocent, but could this be the world formula for streaming? Yeah, don't know yet. But the thing is, so I'm still not convinced completely, but I'm getting there. So, but it's interesting. So, because, I mean, like I said, I was a former researcher, and I like Occam's razor and like removing concepts if you don't need them, and I like clean stuff, right? So you see all these concepts which we had before from Kafka Streams and Flink, and you can basically get rid of them. You don't have to learn them anymore if you build a system on DBSP. Of course, I mean, there are some trade-offs here and there, but basically it's a huge improvement in just simplicity, which amounts to saving money in the end, I guess. Not yet with my tool, it's not finished. Yeah, but basically, yeah, you can, so for example, let's go through some of them. Co-partitioning, I mean, basically, Kafka is just put on top. So in my tool, for example, it could be any input, but it happens to be Kafka. But partitions do not play a role because inside the stream processing system we have sets. We don't have these lists. So it doesn't matter in which order the messages arrive, actually, right? So because if you have some key on them, something which makes them unique, you don't care. Keying, so for example, in Kafka Streams, you have like heavy restrictions when you want to join, for example. I mean, there's foreign key joins now, but it's still kind of awkward, right? Keying, I mean, in DBSP or in this, in Kafi Streams now, we turn to Kafi Streams a bit more. In Kafi Streams, I mean, a message is a message, a Kafka message, with timestamp, headers, partition, offset, key, and value. And you just select anything for that, for your index, right? For your join index, for example. And so on and so forth, right? I mean, something is not, especially time windows, watermarks, spill to disk, you'll see that later. So Kafi Streams is not quite ready, but I think it's possible. It's a hobby project after all. So, yeah, what is Kafi Streams? Kafi Streams basically is, like I said, a Python library, which you can download on PyPy tomorrow, maybe, today. And it's based on Bruno's Python implementation of DBSP. So I didn't do any of this magic, really. It's his. And that's kind of the second DBSP implementation that exists, right? So second bigger one. So there's the big one by Feldera, by the original inventors in Rust, which is that one. But there's, yeah, and then there's only PyDBSP so far. You could also do this in Java. I mean, it doesn't really matter. You just need a hash map, essentially, after all. Yeah, like I said, it's heavily inspired by Kafka Streams. And yeah, so let's start. We start with the word count example, which sounds very relational and databasey. No. But yeah, just to see how it looks like, right? So there's some boilerplate around it, but essentially what you do in Kafi Streams, you build a topology. So that doesn't depend on Kafka at all. You just build a topology for stream processing, which looks a bit like Kafka Streams. So you say, okay, I want to have a source node. TN always stands for topology node. That's the main class. And then you have a Fluent API, a bit like Kafka Streams, right? So you say, I take this source, I do a flat map, in this case where so this example is about like imagine you have a Kafka topic where you have values which are words, text, like lines of text. You want to split up these lines of text into words and then count how many words you have. So this is why we use split here to split this line into multiple words. Flat map is kind of an explode in database lingo. So out of one message you make many messages. then this gets a bit low level here just for this example. So integrate means you sum up the weights, and map basically gets these weights from the z-sets out into the count, into the actual record which you put into the sink, because otherwise the weights are hidden. Right, so let's see how this looks like. So this is the topology basically. So it doesn't work. Can't copy it. So wait a sec. There was something missing. So this is, yeah, it's a very simple topology. You can see it on the right here. Yeah, very flat. So you have the source, that's the lines of text, this explode operation or flat map, integrate and map. Now, what will happen? So this is again some more boilerplate stuff. So we feed it with this line of text multiple times. So that's hello, hello, Kafi Streams. And yeah, so this is the code from before where we built this topology. And then what remains to be done is just, I mean, in each step, push new data from the data source into the stream processor, and latest basically does one step forward inside the stream processor and prints it out. So after one step, we see that because hello is twice in there, hello has count 2, Kafi has count 1, streams count 1. We do one more step. Hello count 4, 2, 2, it's the double. Now we do something interesting, we do a retraction. And try to do this in the Kafka Streams word code example, it will be hard. We say just, this is a retraction, so I want to remove one of these lines again. And then you see that the word count, oh, here, gets back to the state before. Okay, now for a more involved example. So this was word count, just very, very basic. But this was more for showing you how it works internally with these z-sets and weights and stuff. Actually, again, back to Hubert and my book, we found out, or actually before I read this, we found out about this blog post, which you actually should read. It's really interesting. It's from 5 years ago now, from Jamie Brandon. It's called Internal Consistency in Streaming Systems. And it has a nice example, which basically, it's a bit contrived, but it completely breaks classical stream processing. So let's see. So this is the example. It's imagine you have, it's also in the book, and yeah. So you have a bank with 10 bank accounts. So pretty tiny bank actually. And each of these bank accounts always does a transfer of $1 from its bank account to another bank account. Right, that's it. So this is the input stream. You have a from account to account, and the amount is always 1. So on this we spin up, for example, in Flink SQL, these views. So the first view is credits, which is the sum of the money that you got, right, from another account. That's a group by here. Debits is the other way around, the money you send away to the other account. Then we do a join, where we basically put together the two views which we created before and say, okay, the balance of that account is the credits minus the debits. So this is basically joined by the account ID or account number. And now comes the even harder part for the classical stream processing stuff. You do a sum of all the balances. Now, in this contrived example, no money gets lost, no money gets added into the system, basically. It's just accounts sending to each other. So the sum of that should always be 0. It should never change. now we try to get, how much time do I have? 50 minutes still? Ah, cool. Then I can run the example on Flink. I'm sorry, but it's so much fun. All right. I'm giving away the. No, can I see? Yes. Okay. So let's clean up the topic first. So also this one. Nah. Too nervous. Now that's my local Kafka cluster. Now it's empty. Now what we do, we run exactly this example in Flink SQL, right? So where is it? So yeah, so it's exactly the same, right? So you have a Kafka source this time. The Kafka sink, I use upsert Kafka, so it should be even nicer for Flink. Yeah, so that's it. Same SQL. No configuration, nothing. It's just Flink 2.2 bare bone. No configuration done. Just defaults. And now, I hope it works, because I've built kind of a test suite also for Flink for comparison. So we send like, I don't know, 100K or so records on Kafka, and then let Flink process it with this job, which, yeah. So now it's starting. We can also go to Flink maybe. It's here. But I'm not a Flink expert. I'm just mean to Flink, but I'm not an expert. Yeah, it's there. Yeah, you see, now all the messages are coming onto the source topic, transactions. And now, what would be the expected result in this example, right? Like I said, actually one message with total null, 0. Now we see what Flink does. Already 85,000. 96. Yeah, it grows and grows. So, and imagine you push that downstream while Kafka connect to some database or some slow old system. So it's a lot of data volume. It's also expensive. But not only that. In this example, this is why, yeah, it's a very mean example for Flink. I mean, Flink isn't so bad. For most others, it works, but yeah, don't know. But it's a very mean example, so I'm very sorry for any. There must be many Flink aficionados here. But yeah, let's have a look at some messages here. So we have like now, let's say 10 messages from 200K. So this tool is not really built for the demo. No time. Not L. Cut. And it's even worse. X and cut. You see, it's changing all the time, right? It's not always 0. It's sometimes 4, sometimes 5. It gets even higher sometimes, right? Yeah, and it goes on and on. So we stop it. But that's the behavior of Flink when you don't do any. I mean, you can switch on multi-batch. You can do multi-join. You can do. I mean, you can fix it. But if you just do it with bare bones Flink, it breaks it. Yeah, I'm printing money for Confluent as well, yeah. Yeah, so that's the picture from the blog post. So that's kind of what you get. Like, so in the middle, so this is the 0. And when you stop the stream, it ends up with 0. I mean, that's eventual consistency in its pure form, right? It ends up with, it is eventually consistent, but only if you stop the stream. But you don't know for how long. So basically all the intermediate results, you're not sure whether they're right, they're mostly wrong. And this is weird. And this got me started on all this actually 3.5 years ago or 3 years ago. Now let's put Kafi Streams on that. Let's first build the topology for that. As I said, I don't like SQL. I didn't say that yet, but I don't like SQL, and I like Kafka Streams, so this looks a bit more like Kafka Streams. And it's not just because of the syntax, it's not SQL versus Fluent API. It's also because you have the freedom to do stuff like code within the topology, like in Kafka Streams. So as you can see here, in all these functions, like there's always lambda functions, which means you can put in any Python code here, right, in the individual steps. Right, so this is basically the same SQL in Kafi Streams. Yeah, so basically very much the same. We build it. This is a generator now. So in the examples here, which I show here, I don't use the Kafka wrapper around it. It's just in memory, so it makes it easier. Of course, with Kafi Streams, you can also do it with Kafka. So you can have Kafka topics, and then they go into the system, they go to a Kafka sync. Right. Okay. Now, let's do this. So we have to create this topology first. And now what we do is we create 100 messages, 100 randomized transactions, and see what comes out. And 0. But this is not the only thing, because when you rerun it, you put another 100, another 100, another 100, and so on. Nothing comes out. The result is always 0 because there's no update, there's no delta here, because the sum is 0, right? And that's how it works, right? So you could save a lot of money with downstream systems and Flink state stores if that would be finished. It's, like I said, disclaimer. Okay. Another nice thing about this. So Bruno, in his latest PyDBSP implementation, so he did a lot in the last 4 weeks, and I had to come after it, so that's why the presentation is a bit ad hoc, but yeah. But he did a great garbage collection thing, which I still don't understand. It's extremely involved, but it's cool. Yeah, so, and where is it? Here. So when I run this, I do the same. So I throw the same amount of messages, which I threw on Flink over Kafka. I throw this at Kafi Streams, or the inner logic of Kafka Streams. And I measure the memory, which is consumed by the state store in a way. It's not a state store, it's basically just an object. But yeah, I measure the memory which I take. And now, and because in this example, everything kind of evens out, right? So that you always have this +1, -1 all the time. And what you see here, it was too fast to see actually, but what you see is the memory stays constant, right? So you have 100K messages which went through this topology now. And the memory is always 127 kilobytes, right? So it's not that DBSP is just using more memory. It's yeah, it's smart, actually, right? So now you can try it yourself. So this notebook is already on GitHub. Like I said, Kafi Streams is still in kind of an experimental state. Unfortunately, I wanted to have it further polished until today, but no way. Yeah, so you can go to the GitHub and check it out. Go through this notebook yourself. Do the Flink examples, for example. There's also examples where I show you. No, there's no documentation really, but you can see how it works with Kafka as well. So test streams gives you, so topology node is the thing I showed you, the wrapper on top of PyDBSP, and then there's another small wrapper which puts Kafka around it, also including snapshotting even. And so what you do here, you set up a connection to a Kafka cluster, in this case local. You create the same topology like before. And then 5 minutes, okay. And then the primitive is run streams. And this basically gives you this Kafka wrapper around what I showed you before, which was without Kafka. So we can do the same example. Which is now going through. Oh, no, it doesn't work. Sorry. I didn't test this. Anyway, so at least I will fix the examples before tomorrow. Yep. Yeah, so what's in it already? There's, like I said, I mean, it's built on Kafi, which already exists for a couple of years. I presented it at different currents and different countries already, Bangalore, Austin, San Jose. This has support for schema registry, REST proxy, everything. Like I said, support for Kafka sources and sinks, snapshotting. There's even some early Debusium input-output support. But yeah, it's like I said, it's a hobby project more or less. And you don't need all this. And the biggest pain points are so far, which I'm aware of, is like time windows need to be supported, and that's not quite so easy. It is possible. Feldera did it to add this to a relational engine, but you need it for like big transactional data when you really have to garbage collect old data. I mean, no way around it. Spill to disk is not available yet. There's this checkpointing, but once your memory runs full, you're done. Multi-core support as well. Multi-core support is already supported by PyDBSP, so that could be done. Real horizontal scaling, I don't know. That is possible in DBSP, not as much as Flink, but it is possible. But yeah, that's too much for a hobby project, I think. Or actually a project for low volume data or medium volume data, right? Yeah, so because the thing is, I built this kind of on the side, but for my company. So I'm working for a retailer in Switzerland, and what I see there, we have 700 users on the platform. The volume of data which is actually being used usually is tiny, and for them, this would already help when it's released in that state. For many, many use cases, and I guess for many other companies as well. It's like extremely simple. So, that's it. Thanks a lot.
Thank you, Ralph. We have a couple of minutes for questions. Anyone any questions? Yep. Mm-hmm.
Thank you for your talk. That was very interesting. I was wondering if in these examples that you have been shown, you are showing subtraction and addition on integer numbers.
Yeah.
I guess that's because these numbers and operations have a special property. Is this library limited to in the aggregation result? Is it limited for the result to have certain properties, or is it limited for certain operations? On what circumstances C-sets don't work? What type of result is not able to produce?
Well, I mean, the normal API is you throw in a Kafka message, and with no weight, right? And there's adapters, for example, for Debusium. When a Debusium message comes in with create or update, then it's weight 1. If it's a delete, -1, and the same outside. But I mean, you can use it append only usually, also, right? Just using weight 1. But inside the system, all these -1s help you to essentially clean up the system.
So the way is kind of the weight is an abstraction, and edits and changes are encoded on weights, right? Mm-hmm. Mm-hmm.
But it's actually hidden. I mean, the example with word count went a bit deeper, so there was these underscore, integrate underscore, but usually you don't need this. Usually you have just map, group by, join, and you don't even notice the weights. Yeah.
Thank you.
All right, I think we're out of time. So if you have any more questions, just ask offline. Thank you, Ralph.
Thanks.